Okay, so what we've done so far, I'm actually going to share this. Let's see here. So we've done so far the test for divergence, the p-series, geometric series, and the comparison test. So as you can see, those are basically the first four things you're going to look at when you're doing convergence and divergence. We also covered the integral test, which is the 8th one. Tonight, we're going to look at the alternating series test, ratio test, and the root test, the other three. So if you think about it, every problem that we've done so far has stated that it had to be positive to work with it, which means we weren't allowed to have any negative signs in it. So the alternating series test, the root tests, the ratio test, and what's known as absolute convergence or absolute convergence and conditional convergence will allow us to work with things that have negative signs in them. So the first and the easiest one is known as the alternating series test. However, this means there's a couple conditions that it has to satisfy to do this. Just as with every other test that you've noticed. This is why integral test is the last one, because for the most part, the integral test you can use. As long as it's decreasing, you're fine. And if it wasn't decreasing, it's going to fail the test for divergence. So these have conditions on them that say if it fits this, we can use this test. Just makes our life easier. The alternating series test has to be alternating. That sounds stupid to say because that's the name of the test, but it's important. The signs have to go either other. So it has to be positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, and so on and so forth. It can't be negative, negative, positive, positive, negative, negative. That's not alternating. Okay, so it's got to go alternating. That's the first big one. If it does that, then we start looking at saying, okay, maybe we can use the alternating series test. The two conditions that it has to fit is, actually, I'm going to swap these two. Just it doesn't make a difference, but I'm going to talk about the second one. This right there, that's in essence the test for divergence. What does the test for divergence say? If it doesn't equal 0, it's divergence, right? So this is basically that. So I would do that test first. You're not doing it on the negative piece. You're just doing it on the positive part. Okay? So because it's alternating, we can ignore that alternating part for a minute. And we're just going to look at that series. So just to be the end. So if it equals 0, we're good. Let's keep moving on to the alternating series test. If it doesn't, you just did the test for divergence, and it fails the test for, or passes the test for divergence, and it diverges. Okay, because that's got to equal 0 for it to fail the test for divergence. The second one is it's got to be decreasing. And just like we did with the integral test, the decreasing part sometimes is the hard part. All right, it's got to be decreasing from term to term. And again, we're looking at, so the big thing with doing the alternating series test is we're looking at this part right here. I can basically ignore that when I'm doing the alternating series test. That piece right there says I can do the alternating series test. Once I've know I can use it, then I'm just using the actual sequence, the BN stuff, to do these two tests here. Okay. Hello. All right. Any questions on the conditions? All right. Let's look at a couple examples. The first one we're going to look at, the harmonic series. Does it converge or diverge? It diverges, right? That's one of those special cases. It's the one. It's that piece. It's basically a p series where p equals 1, So it diverges. This is the alternating harmonic series. It's the exact same thing, except it goes negative, positive, negative, positive, or positive, negative, positive, negative. So let's look at it in terms of the alternating series test. So, 1. Is it alternating? Yes. Okay, good. So I can use this test. 2. Is the limit as n goes to infinity of Bn equal to zero? So that we're looking at so in this case, Bn is 1 over n. So as n gets infinitely large, does that go to 0? Yes. The sum doesn't go to 0. That's why the harmonic series diverges. But Bn, that sequence, the limit of it does go to 0. So yes. And the last one is Bn plus 1 less than or equal to Bn? So is 1 over n plus 1 less than or equal to 1 over n? Is that true? Yes. This side's bigger, the bottom's bigger, right? Therefore, it's got to be smaller. So yes. So this converges. All 3 yeses means converges. If any of them was a no, we can't use this test. I said something quickly that was very important. If they're all yeses, it converges. If any of them are no, we cannot use this test. Notice I did not say it diverges. The alternating series test does not tell me if it diverges. The alternating series test only tells me it converges. However, that one right there, or the one I did second, is your test for divergence. So if it fails that test, you then basically showed that the test for divergence shows it diverges. Okay, and that would have been the test you actually used to show divergence, not the alternating series test. Okay. Does that make sense? Because that's really sometimes that's the hardest part, where you'll do a test, it'll fail the test, and you'll assume it just diverges. Okay, you can't use that. So you have to look at what the test actually shows. And most of these tests only show convergence. There's a few that show divergence, but most of them only show convergence. Or you have to do something different to it to show that it converges or diverges. All right, so let's look at this one. Since this is still technically working with the alternating series test, we're going to assume it's alternating for a second. All right. So, is this series alternating? So this right here, that's the -1 part, right? So it's -1 to the n, which means every even power is going to be positive, every odd power is going to be negative. Therefore, every other power is going to alternate. So yes, it alternates. So now we can look at Bn. So Bn is just 3n over 4n minus 1. is the limit of that as n goes to infinity. What's the limit of this as it goes to that? So how am I going to find the limit of this one? So I'm going to divide everything by n. So I've got 3 on the top and then 4 on the bottom. Because 4 minus 0 is 4. So does this limit equal 0? No. So I cannot use the alternating series test. I don't even have to check this one. I don't have to worry about that. Even if that one's true, it doesn't matter. As soon as you get a no, you can stop. So I can't use the alternating series test. Since it failed this one, remember the test for divergence says the limit as n goes to infinity of Bn does not equal 0, which I just did, and it equals 3/4. So therefore, it diverges based on the test for divergence. The nice thing is most of these tests you can just abbreviate with the letters and I'll know which one you're talking about. Like alternating series tests, you'll see me put AST all the time. Test for divergence, you could just put TFD or TD or whichever way you want to write it. Like there's not ones that. Okay. But somewhere, so when you do your test, this is how I'd want to see it. Okay. Now, you could have looked at this and done the test for divergence first. Like that's possible. You could look at it and go, okay, I know that Bn diverges, so it's a test for divergence, and I didn't worry about the alternating series test. All right. But if you started the alternating series test, that's not a bad thing. If it's alternating, the second thing you're going to do is the test for divergence anyway. So it's not like it's a horrible thing to start with the alternating series test if the negative one, you know that its sign goes back and forth. All right. Let's look at this one. All right. So, is it alternating? Yes. So, let's try the alternating series test. So, is the limit, so in this case, actually, I'll pull it. Once it's alternating, you could say, okay, what Bn is. So that's n squared over n to the third plus 1. So does the limit as n goes to infinity of n squared over n to the third plus 1, what does that equal? So in this case, I divide them all by what? N to the third. Whatever the biggest on the bottom is. So I get 0 over 1, which is 0. So that checks off. And it's alternating because of that. So that's the alternating check. So the next thing we have to show is that bn plus 1 is less than or equal to bn. So we have to show that this is decreasing. So this one's a little harder to show that it's decreasing, just because more than one thing changes. So like the one we did before, 1 over n plus 1 is obviously less than 1 over n. But in this case, I've got n plus 1. So if I set it up, I'd have n plus 1 squared over n plus 1 to the third plus 1 is less than or equal to n squared over n to the third plus 1. And it's kind of hard to be able to, like, just looking and go, yep, that decreases. If you can't do it just by looking at it, it's not extremely obvious, find the derivative. Because when we find the derivative, I can, as long as my derivative is negative, it's decreasing. So we're going to take this and find my derivative. Did you get it all? You want me to go back? Okay. All right. So, what's the quotient rule? It doesn't. It's the derivative. It's low d high. Derivative of the top times the bottom minus the derivative of the bottom times the top.
Oh, it's not the quotient, the derivative.
Yeah, it's the derivative quotient. Was it high d low and low d high? Yeah.
And then it's over g prime.
Yeah, it's
minus.
It's easier to write. I know, because especially when you have to do this down the bottom. I just literally happen to be writing this a million times in my book that I'm writing. So, all right. So basically, find the derivative of the top and the bottom, and then we plug them in. So,
I'm sorry, what's the exponent of g?
2, it's squared. Because you square the bottom. So derivative of 2n or n squared is 2n. And the derivative of g prime is 3n squared. So I have, and you can do this in x's, or actually, we really should do them in x's just to make our lives easier. Because I'm going to end up making an x over here at some point. So 2x times x to the third plus 1 minus 3x squared times x squared all over x to the third plus 1 squared. So I have, if we look at this, can the bottom ever be negative? Because we're looking for this to be less than 0. Right? So since the bottom can never be negative, the top is what I got to look at. So all I'm going to look at now is I'm only going to deal with the top, because that's all I have to worry about. So I've got 2x to the fourth plus 2x minus 3x to the fourth. So I've got 2x minus x to the fourth has to be less than 0. If I factor this one, because it'll make my life easier, multiplication always makes life easier when you're Dealing with it. So I got x times 2x, 2 minus x to the third. Has to be less than 0. So I've got x is less than 0. And I've got 2 minus x to the third is less than 0. So I've got x is less than 0 and x is greater than the cubed root of 2 is when it's going to be, the derivative is going to be negative. Yes. Can my n ever be less than 0? When we're doing series? Where does n start normally? At 1. So, and it goes by whole numbers, right? So it's never going to be less than 0. So I don't have to worry about the x is less than 0. So it's going to be decreasing when x is greater than the cubed root of 2. Okay. Just like the problem when it was decreasing when it was greater than e, as long as it's going to decrease at some point, like generally decrease, we can use the problem. So bn plus or 1 is less than or equal to bn. So this shows that it decreases. So that works. So therefore, this series converges. Yes. No. Okay. Because you'd have to test them all. Because the goal when you're looking at this isn't necessarily to find out if it is decreasing right at the beginning. The thing you're trying to find is, does it do anything funky down the line? Okay? So like we could have problems that look like they would work perfectly fine. That'd be negative from 0 to 50. And then from 51 to 75, it's increasing. So if you just randomly try some numbers, you might not catch that spot. So the derivative would catch that spot. You'd see at some point it's like, okay, well, it's decreasing from here to here, and also from here, but not in between. So you caught that part when you were doing the derivative. So that's the purpose of doing the derivative. That's also why that's not 0. It's not 1. So it's like I'm not necessarily worried about it decreasing. And this one actually does decrease from 1 to 2 because that's in between 1 and 2. But like if it goes to E is at 2.7. So it could be increasing from 1 to 2, but from 2 to 3 it's decreasing, and every point after that it's still decreasing. So we're fine to use the tests. Okay. Does that make sense? All right. So this one, because it passes all 3 alternating series test rules, it converges. All right. So the next thing we're going to look at is what's known as absolutely convergent. This isn't necessarily a test. But what this does is if the positive version of it works, then all the alternating parts also work. Okay? But if the positive one doesn't work, it doesn't tell me anything about the negative ones. That's what we're going to see in a second. So absolute convergence states that the series of absolute values is convergent. So if I take the absolute value of them, and that's convergent, therefore the series in general is convergent. Any variation of that. This solves the problem where I was saying a little bit ago at the beginning where the alternating series has to be alternating. But let's say we're looking for a series of cosine. It was cosine of x. Does cosine of x have, or cosine of n have positive and negative numbers? Yes. Are they alternating? No. Okay. So, for example, cosine would be 1 would be positive, 2 and 3. No, 2 is negative, then 3 and 1, or 3 and 4 positive. It like jumps back and forth as long as we're looking at radians. So it's not alternating. So we couldn't use the alternating series test on that because it doesn't go back and forth. But if we look at the absolute value of it, if that works, then we're good. Okay. So let's look at a couple problems. All right. So this one. So if we look at this problem here and we take the absolute value of it, this is the same thing as saying 1 over n squared. Okay. So I took the absolute value of my series, and it's the same thing. That's the same thing as saying 1 over n squared. What about 1 over n squared? Is that what test does this fall under? That's a p series, right? And in this case, p equals 2, which is greater than 1. So therefore, it converges. So this series is known as absolutely convergent. Which means any series that goes down to that, when I take the absolute value of it, would be convergent. Okay. What if I did the series that? If I take the absolute value of it, if I do the absolute value of this, it goes to 1 over n, right? And that does what? Huh? That's the harmonic series, which is, this is divergent. That tells me nothing. Okay? Because that's divergent, and we actually know that this series right here, that's convergent. Right? Because that's the alternating harmonic series that we just did beginning of class. Okay? So again, it goes back to the whole thing. Most of these rules tell me what happens when it's convergent. They don't always tell me what happens when it's divergent. So if it converges, I know it's absolutely convergent and every possible option works. If it's divergent, it doesn't tell me it's absolutely divergent. It tells me that it could be conditionally convergent if some of the other ones do work. But you have to test those individually at that point. Okay, so it's one of those things that If it becomes absolutely convergent, it's great. It helps me out a ton. It's going to solve a lot of other issues. If it comes out to be divergent, we have to try something else. Let's try this one. We're talking about the cosines. So let's look at this one. All right, so my series that I'm basically looking at is cosine of n over n squared. As it sits, this switches back and forth, but it doesn't alternate. Okay. And depending on if n in this case is going to be radians or degrees, depends on where it switches. So as it sits right now, it doesn't fit the alternating series test. So let's try the absolute value. See if it's absolutely convergent. Okay. So if I took the absolute value of this, we're now looking at the series, the absolute value of cosine of n over n squared. Unlike the last couple problems where when I did the absolute value disappeared, because in essence it was just getting rid of the negative sign that was there. This one I can't get rid of the absolute value because cosine doesn't switch constantly. I still need to find the absolute value of that. So we need to show that that is convergent or divergent. That's what we're looking at. So what does this look like? So first, let's go through it. We don't know if it necessarily fits the test for divergence because I'd have to actually do that. And because it's cosine and stuff in there, that's a little more complicated to figure out if this limit goes to 0 or not. So we're not going to do that. That's one of those things. Like when you're looking through the rules, look for ones that are easier to work with. Like even though the test for divergence is the first thing that's in the list, that's not always going to be the easiest way to work on a problem. It's just one of the first things we want to look for. Is it a p-series? I'm seeing hesitation. Okay, so why am I hearing yes and no? There's a reason for it, and that's fine. Why would some people say yes and some people say no? Okay, so there's an n squared in the bottom, which kind of makes sense for a p-series, right? But there's a cosine on top, which is not a p-series, right? It's got to be a 1 or a single number, right? Okay, so if it's not a p-series, but it's kind of like a p-series, what did we do last class that we could possibly use? The comparison test. So let's look at those comparison tests. Let's see if I can compare it to a p-series. Okay. So the p-series that you'd want to compare it to would be 1 over n squared, because that we know. So I've got cosine of the absolute value of cosine of n over n squared, and I want to compare it to 1 over n squared. The bottom didn't change, right? Just the top did. Is the absolute value of cosine of n less than or equal to 1 or greater than or equal to 1? Cosine's going to be always less than, right? It goes between cosine, the absolute value of cosine of n is less than or equal to 1. Because it's between 1 and -1. So that would be like that, right? The order of that is important because if it goes the other direction, then we're looking at something different, correct? This series right here, I know converges because P is 2, which is greater than 1. And this is always less than it, right? So that means that has to converge. So this series right here is what? It's absolutely convergent. I think I've written absolutely different every single time I've written on this board. One of these times I think I'll get it spelled right. This is why I abbreviate things. All right, so in essence, actually, that means it doesn't matter if this is in radians or degrees, it's still convergent. Because radians and degrees will give me two different answers. Because if this was in degrees, 1 through 90 is going to be positive on the cosine. 90 through 270 is going to be negative. Okay, so, and if it was in radians, 1 would be positive. 2 is between 2 pi and, nope. Well, yeah, 2 pi. 2 is between those two, so it'd be negative. And then it goes positive and then positive. So it's like it jumps back and forth. But it doesn't matter because we've stated that it's absolutely convergent, and that means any variation of signs on the top will still be convergent. Okay? Does that make sense? All right. I'm going to have you guys try one before I go to the last two tests. All right. Try that one. Step one, is this alternating? Why? Okay. So if we eliminated that, is it always positive? So the question, so this one, got to remember, most problems, this isn't an issue because most functions don't alternate. Trig functions do. Okay. So in most problems, if you see that, you're absolutely right. You're good. Because what's after it is not going to alternate. However, sign does alternate. Sign does go from positive to negative and back and forth, right? The question is, does that? So where is sign positive? So sign is positive between 0 and pi, right? Cosine 0 to pi over 2. So between 0 and pi, it's positive. Okay. So if n is 1, this is 0, correct? Because pi over n is 0. Or pi over 1 is, sine of pi is 0. If n is 2, is it positive? It's pi over 2, right? If n is 3, is it positive? Well, there ever be a situation where this is going to be negative? Or is that number right there always going to be between 0 and 1? That's always going to be between 0 and pi, right? Okay, so it's fine. But in this situation, you actually have to show that. Okay? That's why I chose this one, because I wanted to have that conversation. So, no, you just have to show. It's like, in this case, sine is positive between 0 and pi, right? Pi over n is always less than or equal to pi and greater than or equal to 0. It's between there. So since the number that I'm using is always between 0 and pi, it's always positive. So we're good. Because as long as that's positive, that does alternate. The problem would be is if they're both negative, that would cancel out the negative sign that's alternating. And I'd end up with a situation where we're negative, positive, 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 like that. And that would cause a problem because then it wouldn't be alternating. But since the second part, the second multiple in this case is always positive, it doesn't matter. Okay? All right. That's the key piece there. All right, so we know it's alternating. Good. Does sine of pi over n, the limit as n goes to infinity, go to 0? So remember this one, we can look at it. One of the rules for limits was I can move the limit inside, correct? So I can look at it this way. So that right there, that goes to 0. And sine of 0 equals 0. So that's good. Yes, it would be kind of difficult to look at the limit as of sine pi over n going to 0. That might be, but remember, we can move the limit inside because that's a function. It's not necessarily, it's not in essence, it's not the chain rule per se, but it's along those lines, yeah. One of the rules we looked at in 11.1 when we were doing just the series was if it was a continuous function, we could move the limit inside. We also could break the limit apart, look at each one individually, those type of things. But this is one of those ones where moving it inside really does help me figure out the answer. All right, so last piece. I have to show that sine of pi n plus 1 is less than or equal to sine of pi over n. Is that true? If the top stays the same and the bottom's getting bigger, then what's happening to the fraction? It's getting smaller. So that's also true. So this converges based on the alternating series test.
Right, it only works with the sine. If it was cosine of both of these values.
So yeah, if it was cosine, it would be a little different. Because cosine's positive between 0 and pi over 2. So
Well, just considering like the fraction.
oh yeah, the fraction part that also would you'd have to look at it in terms of that one. That's why when we did the cosine, when we did the absolute value of it. And it really just depends on the problem. Sometimes like this one might not work for cosine. But yeah, because cosine's getting bigger. It's the opposite. If it was pi over n and pi over n plus 1, cosine would be bigger. So yeah, cosine would fail this test. And we'd have to use something else. No. See, Scott, no. It wouldn't divert. Well, it might, but we don't know that from this test if we did cosine.
But yeah, no, I know that.
So you have to be careful because honestly, that's the fastest thing like people will do. Like, oh, it failed the test, it must diverge. Make sure you look at it. All right, 2 more tests. So we've got the ratio test. And the root test is the other one we're going to look at. So the ratio and the root test are actually one of the few tests that will tell me if it converges or diverges. But there's a third thing here where it doesn't tell me anything. So it helps us at one end. If something happens, then it still doesn't work. And I'm going to go through and do problems with this. You'll see how it works. If the limit of these a to the n plus 1 over a to the n is less than 1, it's converted. Or it's absolutely converted. And it's absolutely because we're doing the absolute value. So these do not matter with the sign. If it is greater than 1 or goes to infinity, then it is divergent. The nice thing, it does tell me if it's divergent. If it equals 1, it tells me nothing. And I have to try something else. Okay. So unlike the other ones where we're looking at the limit going to 0, this one we're looking at the limits around 1. If it's less than 1, it's absolutely convergent. If it's greater than 1, it's divergent. And if it equals 1, it's inconclusive. It'll never be negative because we're doing the absolute value of it. So we won't have a negative. That's why I don't have to worry about from -1 to 1, for example. If it was to equal 0, what would it be? It'd be less than 1, so it'd be convergent. Okay. The ratio test works really well for problems that look like this. If I was to, before I showed you the ratio test and asked you, told you that we're probably going to do problems with it, if you were to look at this, what's some of the things you'd look at and notice? Yeah, it's kind of got the top end of the third that kind of looks like a Pew series, right? And if that was alone just on the top, we know it diverges because that'd be bigger on the top. And the bottom kind of looks like a geometric series, which would be great if they were both geometric. I could put them together, but they're not. So we can't do either of those rules. So the ratio test kind of works on these type of problems where it's kind of ambiguous and they're not easily to look or easy to throw into a specific category. And trying to do the derivative of this, or I mean the integral of this, would also be kind of difficult. So let's look at the ratio test. All right, so the ratio tests, all of them said the same thing. It is the limit as n goes to infinity of the absolute value of a to the n over a to the n. So I have n plus 1 to the third power over 3 to the n plus 1 divided by n to the third over 3n. Notice I did not put that there, although you should, because in essence, that the absolute value takes care of that. The only time you'd have to put the absolute value still in place is if it was a trig function that does go back and forth. All right, so now we've got this mess that we've got to clean up. When I'm dividing fractions, how do I do it? Keep change flip. So I've got n plus 1 to the third over 3 to the n plus 1 times 3 to the n over n to the third. So we've got to kind of figure out some way to cancel some stuff out so I get rid of things. This right here is where you want to look. 3 to the n plus 1 is the same thing as saying 3 to the n times 3. Because remember that when you're adding one, when you're multiplying like bases, you just add the exponents, right? So 3 to the n times 3 is the same as 3 to the n plus 1. Which means now I can cancel out those two. So this becomes 1/3. And then I have n plus 1 over n to the third power. Because they're both to the third power, so I can combine them and put them together. That looks a lot nicer than what I started with. I can then change this to 1 plus 1 over n to the third power. So as the limit's going to 0 or going to infinity, what's happening? The 1/3 stays the same, right? That 1 stays the same. 1 over n goes to 0. So 1 to the third power is 1 times 1/3 is 1/3. So the limit in this case goes to 1/3. So is it convergent, divergent, or I don't know? It's less than 1, therefore it's convergent. And it's all these are always absolutely convergent. or just divergent. The alternating series test. So the problem with the alternating series test is we got to show three things, right? We got to show that it is it's going to zero. The limit goes to zero, which in this case, that would be kind of difficult to show just because it's n to the third over 3 to the n. So the limit's going to be a little harder to deal with. That's why I said we didn't necessarily look at the test for divergence. And we also have to show that n to the third over 3 to the n is greater than n plus 1 to the third over 3 to the n plus 1, which also might be kind of difficult to show. So this test actually is easier than showing those other couple things. The alternating series test works really well when you have one type of problem in it. When you start to combine a bunch of different things like this puts in the geometric and p-series type stuff together, this one tends to go with the ratio rules a lot easier to deal with. All right, let's look at this one. So you'll notice the two tests, the ratio test and the root test, have a tendency to deal with problems that are crazy looking. Where the other tests work really well with things that we know. Like this one, we have n to the nth power over n factorial. First of all, you never learned how to take derivatives of factorial, so we're not going to be able to do that. You never did the integrals of factorial, so we're probably not going to do the integral test for this one. It's not a p-series. It's not a geometric series. It's not alternating. So as of right now, the only test that you have that you possibly could use would be the ratio test. So let's look at the ratio test. Honestly, the hardest part for you guys when you're looking at the ratio test is the algebra. It's once you get it into the format of the ratio test, how do you simplify it down? Like when we did this problem here, it's realizing that n to 3 to the n plus 1 is the same thing as saying 3 to the n times 3. It's realizing that I can take the two exponents and putting them together. Those are the things that are going to be the hardest things for you to deal with. Is just remembering those little rules. And this one's going to come into the same type of situation. So we're going to do the ratio. So we have n plus 1 to the n plus 1 over n plus 1 factorial divided by n to the n over n factorial. So we have n plus 1 to the n times n plus 1 over n plus 1 times n factorial is n factorial over n to the n. All right, so let's look at how I broke this apart. This, same thing I did with the 3. Whenever you have n plus 1 up in the numerator, you can split it into two parts. You have the n piece, and you have the one with just the 1. So that's how I got the n plus 1 to the n, and just the n plus 1. Okay. What's a factorial? We did talk about this briefly. Yeah, factorials are multiplication. So 10 factorials, 10 times 9 times 8 times 7 times 6, all the way down. It's 5 factorials, 5 times 4 times 3 times 2 times 1. So n plus 1 factorial is n plus 1 times n minus 1, n minus 2, all the way down. So in essence, it's n plus 1 times n factorial, because that's one less thing. Okay? The nice thing is these problems, if you're going to see a problem like this, these are the rules you're going to use. So like, it's not going to be something crazy. The only thing that crazy that could happen would be if they gave you n plus 1 factorial in the original problem, and you'd have to do n plus 2 factorial, because then you'd have n plus 2, n plus 1, and then n factorial. But little things like that are hard to figure out when you understand it. And the goal is to find things that we can cancel out. Okay, so now if we look at this, we can cancel things out. So I can cancel out those two. And I can cancel out those two. And I'm left with n plus 1 over n to the nth power, or 1 plus 1 over n to the nth power. So the question is, what does that go to as the limit goes to infinity? This actually goes to e. That is the definition of e. That's so you know how like pi, they have like there's like certain definitions to get you apart. That's actually the definition of e. And it's the limit as n goes to infinity of 1 plus 1 over n to the nth power. And it's not something you would know. It's just one of those things you're going to have to know. Like, there's no obvious thing. Oh yeah, that's e. So because what you'd end up getting inside, if you go to infinity, it's 1 to infinity. The problem is that as 1 over n goes to infinity, it's not 1 to infinity. It's something else going in there, so it actually does not go to 1. Okay, and that's the one thing that I wanted to make sure you didn't get. So you can't, if you plug in infinity to both those, that's why normally you can plug in infinity and it's fine. When you get crazy problems like this, when you try to plug in infinity, it doesn't necessarily work. Remember, we're looking at the limit as it goes to infinity, not at that point. So the 1 over n does go to 0, but as it's getting closer and closer to that, the exponent is getting bigger and bigger, so it's multiplying out. So it actually is going to 2.718 on down the line. So it goes to e. Since this goes to e, does this converge, diverge, or I don't know. This diverges because that is greater than 1. All right.
What test do you want?
Yeah, so this one you'd write the ratio test. I should be able to figure it out from the work you're doing, but some of the tests are like very short in how much work you'd have to do. So yes, definitely tell me which test you're using and show out the work. Since it is a take-home test and since it basically is a true and false type test, if you don't show work, you're not getting any points for the problem, even if you actually guess correctly. So just telling you that. So there has to be some work shown on the problem. And the work has to make sense for what you're doing.
A question.
Yes. Huh? Yes, it's recording. You can tell up at the top, see the little red dot?
Yes.
No red dot means it's not recording. All right. What's this one? This is the harmonic series, and this one does what? This one diverges. So we know this one diverges, right? Okay. I'm going to do a quick ratio test on this just to show you what happens. We know it diverges. We have a rule for it. It's a P series. It's equal to 1, so we know it diverges. But I want to show you the ratio rule with this one because it's important. So we have 1 over n plus 1 divided by 1 over n. So this ends up becoming n over n plus 1. If we divide everything by n, I get 1 over 1 plus 0, which equals 1. Based on the ratio test, that tells me what? I don't know. Okay? It tells me nothing. All right? We know this diverges because of another test. But the ratio test doesn't help me with that. What's this one? This is the P series. This one does what? This converges because it's greater than 2, right? So P equals 2, which is greater than 1, so that converges. And this is where I was saying that sometimes the amount of work you'd have to show is very limited. That's all you'd have to show for that problem, for the test. It's a P series, the rule, and a convergence. That's all you'd have to show for this problem for the test. Okay? So I want to show you the ratio test so you can see something crazy, the thing that makes the ratio test annoying sometimes. So I have 1 over n plus 1 squared over 1 over n squared. So this ends up being n squared over n plus 1 squared. So I've got n over n plus 1 squared. Divide them all by n. So I get 1 over 1 plus 0 squared, which equals 1. So again, based on the ratio test, I don't know. Okay? That's why that 1 doesn't help us. Okay? I just did 2 examples. 1 converges, we know. 1 diverges, we know. The ratio test both comes out to be 1. If that's the case, you have to try something else. Okay? The root test. And before I go any further in this one, if the ratio test does not work, the root test will not work. Okay? So don't go, oh, I got the root test. Let me try that one. If the ratio one doesn't work, the root one does not work, and vice versa. Okay? So these 2 tests, you will never use both. You will only ever use one of them. If it doesn't work for one of these, you have to try one of the other methods. And it might be you have to do the integral test. That's possible. The root test is basically identical to the ratio test. The only difference is we're taking the nth root of the absolute value of it, this series of it. That's that symbol right there that nobody can see. Okay? So the root test, you're just taking the nth root of it. And the rules actually stay the same. If the limit's less than 1, it's absolutely convergent. If the limit is greater than 1, it is divergent. And if it equals 1, it is inconclusive. All right. So the root test works really well when you have problems that look like this. When you have problems that are raised to the nth power. Now, when we have things raised to the nth power, you might think, oh, geometric series, that works really nice. Yes, if it's a single easy number that I can work with the geometric series. If you look inside here, not the simplest thing to make look like a geometric series. Okay. So that's where the root test comes into play. So we're going to take the nth root of the absolute value of 2 plus 3 over 3 to the n plus 2 to the nth power, which just comes out to be 2n plus 3 over 3n plus 2. And now we're looking at the limit as n goes to infinity of that. And what does this limit go to? This one goes to 2/3. Based on the root test, that is less than 1. That's absolutely convergent. Yeah, I just divided everything by n. Actually, this one, I cheated and I just used the pre-calc rule and looked at the leading coefficients. I don't care how you get from here to here as long as that's right and as long as you show me that. So if you don't sit there and divide them all by n's, I'm fine with it. Okay. So that doesn't make a difference to me which way you get there. Just show that that's it. And this part right here, that's you showing the root test. So from that, I know which test you're using. You've shown that it's less than 1, so therefore it's absolutely convergent. All right. It depends on what the question's asking. Like, honestly, as long as you tell me it's convergent in this situation, you're fine. If you're using one like the other ones where you took the absolute value specifically because it was alternating and stuff like that, and you were using absolute convergence to show that the original series was convergent, then you have to tell me that it's absolutely convergent. Because you're not actually testing the original series at that point, you're testing the absolute value of it. Make sense? Okay. All right. Last one. All right, so we've got n plus 1 over n to the nth power. So we want to, let's use, it's to the nth power, something crazy to the nth power. Let's use the root. So this would be just n plus 1 over n. So we're looking at the limit as n goes to infinity of n plus 1 over n, which equals what? It's 1. Mm-mm. Divide them all by n. We get 1 plus 0 over 1, which is 4. All right, so this goes to 1. So the ratio test doesn't, the root test doesn't help me. The ratio test also will not help me. So let's look at the problem. We got to still figure out what the thing is. So if I did the limit as n goes to infinity of just the original problem, that is 1 plus 1 over n to the nth power, which should look familiar considering we did it less than 10 minutes ago. That is what? That is E. Since the limit does not go to 0, this diverges. And this was the test for divergence. Remember, the test for divergence is just, and the limit has to go to 0. If it doesn't go to 0, it diverges. If it goes to 0, I got to try something else. So this is one of those problems that when you originally looked at it, you're going to go, oh, it's the ratio, it's the root test to the nth power. So you try it, and it comes out to be 1, and you're like, okay, I got to try something else. And in this case, the test for divergence really does help. I would have that down on your note card. I'm not, actually, I don't remember if I put that one on the test or not. A 1 + 1 over n to the nth power, but I would have it on your note card just in case, or on a sheet of paper, because I'm going to go off in a limb and none of you are going to sit there and look at a note card while you're sitting at home doing the test, and that's fine. So you can use your notes for it. I would prefer not using Google or asking Bard or ChatGPT to answer. And I would tell you why, because they typically get things wrong. So I would not use them to do your math work yet. Give it a couple months, it probably is going to fix itself. But right now, I would. Honestly, I'm one of those people that, like, I think technology will end up replacing some part of teaching. I think, like, watching videos and stuff like that is great for the second time you hear it, or to refresh something that you've heard in the past and want to learn. It's not necessarily the best way to get it the first time. So, yes.
Well, I was in like typing class.
Yeah. Yeah. We should.
Yeah, no.
Probably
Yeah,
should.
I type very slowly, except when I actually know someone type, and then I can just.
Yeah.
Thinking, well, I think it's just.
Oh, my God.